In topic 6.8, our focus is on solar energy. So we can use solar energy in a few different ways. To start, we're going to talk about what you might be most familiar with solar energy use, and that's photovoltaics. They're often abbreviated PV for photovoltaic. These are special technology that can convert light energy into electricity. Okay? And a photovoltaic cell is, you can see the model here on the right. A photovoltaic cell is a panel of glass on top, layered with some semiconductor layers that are separated by a junction. And when sunlight, energy from light, hits this top layer, you can see in this bottom part of the model, you can see what happens. Energy from light dislodges electrons, which are then free to travel, and those electrons which are freed, their place is taken by other electrons below them. And so this starts this cycle of electrons moving from this negative electrode to the positive electrode, and as they move, they can then power electrical appliances. And so this is how a photovoltaic cell works. And there's lots of variety and different materials that they're made out of, and different types of semiconductors that can be used, but overall the idea is the same. Sunlight dislodges electrons, which then flow, and as they flow, they can power electrical batteries or electric appliances. We'll talk a little bit more about photovoltaics, but they have become increasingly more and more efficient over the last several decades, and they've also become less and less expensive. The use of photovoltaics to generate electricity really is dependent on solar availability, on solar intensity. This map of the United States on the left shows solar irradiance, and so the redder the area, the more incoming solar radiation, and therefore the more useful photovoltaics can be. The less intense the sunlight is, the less electricity that's going to be generated by a PV cell. And so obviously you see is in the sunnier regions of the United States, in the desert areas of the Southwest, this is where photovoltaics can be the most useful. And so this is a complex, and we don't need to get into very much of the details, but this shows what I was talking about, the efficiency of photovoltaic cells over time. So you can see, photovoltaics have been around for a long time, but the y-axis on this graph is the efficiency. How much of the incoming solar radiation is being captured and converted into electricity. And so we see that these are the different types of PV cells. You don't need to know anything about the details. But what the main point of this is that there's been a significant increase. We're getting up to the point where photovoltaics are 40 to 50% efficient, when in some cases they began below 5%. And so as they get more efficient, you need less PV cells to produce electricity. So this is a key component into the adoption of solar generated electricity. And these are the names of some of the different types of technology you can see in different colors. And so with this change in efficiency has also been major changes in the use of solar energy to generate electricity. And we can see for a long, long time, it's basically almost very little power generated by photovoltaics. But as we got into the mid-2000s and on, we see rapid increases, and we can see that shown in this graphic. You can see China has been ramping up installation of photovoltaics to support their economy. And we can see similar trends in the United States and India and other areas, a rapid increase since 2000 or so. And we could also see one of the reasons for that rapid adoption is the prices. This represents how much photovoltaics cost per watt generated, and we could see early on when these panels were first becoming available, it was about $100 per watt, and we can see today we're well below $1 a watt, and continues to increase. So solar photovoltaics, we can see some examples here. You have one in lots of calculators, a tiny little PV cell. calculator doesn't require a lot of electricity, therefore it can power itself using this very small photovoltaic. You can use something, I have one of these that I'll show you in class. This is a sort of photovoltaic cell that you can use. It's portable. It's about enough that you can charge a phone using this kind of photovoltaic. And then we know some people have these photovoltaic cells installed on their rooftops to help generate electricity, and they look like this. There's other kind of versions that look a little bit different, but they offset some of the electricity use of a given household, depending on the location, depending on the amount of incoming solar radiation, etc. These are an interesting version. These have been around for a little while now. These are Tesla solar roof, and what you can see is each of these, it looks like a typical roof, like a shingled roof you might see on a traditional house around here, but actually each of these is a PV cell, and so it looks a lot different. It looks a lot more traditional than having the PV cells installed on your rooftop like we saw on the last slide. And one issue that arises is that you only can get energy from a PV cell if the sun is shining. So what happens when it's dark out? What happens when it's cloudy or wintertime? And so that's a question that often arises, and depending on the location. And one way to, this is sometimes called the intermittency problem, is that the sun's not always shining. Well, there are now battery systems that you can install at your house. This is called the Tesla Powerwall. There's other versions of this where this is basically just a very large battery. And so when you have an excess of electricity during very sunny times, that excess electricity can be stored in the battery, and then when you have less or no sun shining, the energy from this battery can be drawn and used in the household. There are also ways in which, if you have an excess of electricity being generated by a solar panel, you can actually feed it back into the grid, and the national grid, for example, in our area, will then credit you towards any electricity you have to purchase from them. So any excess actually gets sold back to the grid and can be utilized, and you can get a credit from that. So what we looked at so far are basically sort of household size photovoltaics, but there are solar, sometimes they're called solar farms, or large areas of solar panels that are placed in areas to provide clean electricity to the grid. You can have these sort of panels. I've seen a couple of these in our area. There's one on Higby Road as you're driving sort of over into Frankfurt. There's one on a house on the left as you drive towards Frankfurt. There's also one where we pick up our farm share in Sequoia. There's one of these. These are larger solar panels. They're not mounted on rooftops. They're mounted on sort of concrete pillars. And often these can be made to track the sun. So they kind of rotate. Their angle can change so that they can maximize the amount of the intensity of solar radiation. This is in, I guess it's maybe not New Hartford or Westmoreland, I guess. If you drive up 840, past Accelerate, and you keep going like you're going towards Rome, eventually you're going to pass some solar installations. They're on your left. You can see from a satellite image, you can see these are a whole series of solar panels. You can see them a little bit closer here that are generating electricity, and these are becoming more and more common in our area and in many areas to generate clean electricity. There are also some other models of using the sun's energy for useful purposes. These diagrams show what's called concentrated solar. And so what you see here in this area, or in this area here, is concentrated solar. What these are not photovoltaic panels that you see here. These are just basically mirrors. They're mirrors that take the sun's rays and then reflect them and focus them on a tower, which we can see here. And we can see it here. And you can imagine this is almost like a magnifying glass, concentrating. Each of these mirrors is concentrating the solar energy directly on this tower, which then obviously you could guess it gets immensely hot. Okay, it can be over 1,000 degrees Celsius. And so concentrating all of this energy in a very small area can create immense amounts of heat. And that heat can be used in a variety of ways. That heat can be used to manufacture things like cement or steel, things which require very high temperatures. It can be used, also it can be stored and in various types of fuels, like hydrogen, that can then be used in other sources. There can be hydrogen-powered vehicles, or that hydrogen can power things like heavy equipment and so forth. So this is another model of producing energy through the use of solar energy. So there's a couple terms. There's another method of using the sun that's called passive solar energy. So what we've been talking about thus far is active solar energy. Active solar energy uses some sort of electrical or mechanical equipment to generate and store energy. So solar panels, PV panels, are active solar. But there are also, and we see that here, we can see another example. There are special solar collectors that can be installed on a rooftop. I've seen many of these in Costa Rica, where basically you have either a container on top of a roof that contains water, or it can be a panel which water goes through it. But basically you're using solar energy to heat that water for household use, rather than using electric or natural gas to heat up water in a hot water tank. This is another method of using the sun's energy to heat up water, reducing energy use. But that's also active solar. Passive solar is something that's a little bit different. It doesn't use any sort of mechanical equipment or any storage or collection of energy. What it uses is architecture and design and materials to maximize the use of solar energy and to minimize the use of other types of fuel. And so we can see this in this example here. This is a passive solar design for a small house. And what you'll see is, using architectural design, you see there's this overhang in front of this house facing the sun. We also see oftentimes there'll be sort of concrete or some sort of material can absorb heat energy and hold on to it. And so the design of this overhang, the angles and the length of the overhang, are calculated so that in the summertime, when the sun is higher in the sky, this overhang shades the window and the interior of the house. So the sun's radiation, when it's at its peak, most intense, is not actually entering the house because this overhang is shading it. And that would minimize the use of air conditioning in the summertime. However, it's designed so that in the wintertime, because the sun is lower in the sky, this solar energy is able to get into the house because of the different angle, and it comes into the house. It can be stored in concrete, which as it heats up, it can hold on to that heat. And so this is an example of passive solar design, where you have these architectural designs that maximize the use of the sun's energy. Here's another depiction of that, where we have the summer sun angle, which it's being shaded from getting into the house, but then in the winter, the sun is allowed in, and this is designed even to have panels which can absorb as much of that winter solar radiation as possible. So these are examples of passive solar design. So are there downsides to PV and solar electricity? There are some. So we know that photovoltaics produce clean energy. Using a solar panel to generate electricity in a home or for entry into the grid is clean. It doesn't release any pollutants. It's just passively sitting there generating electricity. Solar panels can be more expensive, although given the graphs we just looked at, actually photovoltaics are becoming less expensive. In some cases, depending on the conditions, photovoltaics are actually cheaper than any other source of electricity. But they can be more expensive. Large solar arrays, grid scale solar arrays, take up obviously space, and that can impact habitats where that space is. These are most efficient in the desert, so if you're using large tracts of desert ecosystems to put in a solar array, that can have impacts on that ecosystem. Producing photovoltaics, it does obviously take energy to do that. It also requires certain raw materials, metals, rare earth metals, and the disposal of photovoltaic cells also poses an issue. So there are some downsides. But whenever we're looking at something like this, what we want to look at is sort of what we call a life cycle analysis. Overall, over the entire manufacture and use and disposal of this product, what are its impacts overall in its entire lifetime? And we can see some of that here in this graph. A life cycle assessment of photovoltaic energy versus coal. Okay, we can look at the beginning, the upstream processes. This is actually building the PV cell or building the coal power plant. And we can see that that's where most of this represents the amount of emissions. And so that's where most of the energy in photovoltaics is expended, in the actual production and in the installation of these solar panels. If we look at coal, this is relatively low. Building of the power plant, construction materials, that represents a relatively low percent of the carbon that's being released. But then if we look when they're being operated, the photovoltaic cell emits relatively little carbon dioxide to maintain and to operate it. If we look at the coal power plant, the mining of coal, transport, the actual burning of coal in the power plant, that's the vast majority of the emissions. And then we can look at sort of the final, the decommissioning of the power plant, the reclamation of the land, the disposal of the solar panels. But when we look at overall the lifetime analysis of these photovoltaics versus coal in this analysis, about 40 grams of carbon dioxide are emitted for every kilowatt hour as we take the entire life cycle into account. When we look at the coal power plant, it's around 1,000. So obviously it's much greater, more than 20 times greater in a coal power plant versus the photovoltaics. Sometimes people will try to discount the use and the efficacy of photovoltaics because they say, well, they require manufacture and disposal and these metals. Well, when we look at the overall contribution to climate change and carbon dioxide, they are far more efficient than fossil fuels.